All right, so this is CDA 3103, homework 5, question 3, part 2. It gives us these two numbers. It just wants us to multiply them, and then I guess convert the final result into IEEE-754 floating point representation. So how do we do it? Well, first I would like to convert these two numbers into binary scientific form, just to um, just to make the multiplication a little easier on us, right? Because multiplying these two numbers sounds like a nightmare, right? So let's convert it into an easier form. How do we do it, right? Well, what does each scientific notation number have, right? Well, they all have a sign, right? Positive or negative. They all have an exponent. Think 2 times, or I guess 2 to the power y. We're trying to find y. And then they all have a mantissa, right? So like it'd be 1 point mantissa. I really should have drew an M, but whatever, right? So we got that. We just need to find these values. How do we do it? Well, for the sign, all you have to do is sort of just copy down the most significant bit. So we're looking at x. What is x MSB, right? Its MSB, or its most significant bit, is equal to 0. So I'm just going to copy down that number, 0. Now, what is the exponent of x? It's just going to be the next 8 bits. So don't include this one, but then just count the next 8 bits. So we're just going to copy that over, right? So I got, it looks like 1 0 0 0, and I have 0 1 0 0. This is our binary biased exponent, right? I need to get it to decimal. I need to remove the bias. So let's work with one thing at a time, right? Let's remove, or I guess like let's convert it to decimal, right? How do we do that? Well, I noticed that the 2 to the 0 bit is off, the 2 to the 1 bit is off, but the 2 to the 2 bit is on. So I'll say this is equal to 2 to the 2 plus the 3 bit is off, the 4, the 5, the 6 are off, the 2 to the 7 bit is on, right? So I'm going to add that. What is that all equal to? It's all equal to 4 plus 128, and that's equal to 132. But remember, I said we wanted to make this a decimal number, and we wanted to remove the bias. How do we remove the bias now that we have a decimal number? Well, all you have to do is just do 132 minus 127. 127 represents the bias, so we're just getting rid of that bias, right? So this is really equal to 5. So that is the exponent for x. Now, how do I find my mantissa? All I have to do is sort of copy down the bits that I didn't already use, right? So the next couple of bits is right here, right? But we have 16 bits that are just set to 0 without a 1 in sight, right? So we don't really have to copy these numbers down because they will be insignificant or really inconsequential to our final result, right? So not copying down these numbers isn't going to change our result at all. So I'm just going to omit these and just copy down the bits that matter, right? So we stopped at this bit, so I want to copy down these zeros and these ones because these zeros are useless, right? So our mantissa is 0 0 0 1 1 1 1. Now how do I use these values, right? How do I use them to make x into a scientific notation number? Well, here's what I'll do. First, we have to sort of apply the implied one, right? So there's always that one here. So that one and then dot. The dot's the binary point, right? So I always have that one point, and then right next to the point, I'm going to append my mantissa. So I'm basically just going to copy it down. So I got 0 0 0 1 1 1 1, and then I had to multiply it by 2, raised to the exponent, so raised to the 5, right? So then now x is in a scientific notation. Now I just have to do the same thing with y, right? So what does y have? It has a sign. And by the way, the sign being equal to 0 here is just saying that x is positive, right? So sign is equal to something, e, right? E for exponent. then M for mantissa, right? So let's go ahead and find these three values. The sign, we do the same thing. We look at the MSB of Y. We notice that it's 0. We copy it down, right? That's equal to 0. What is the exponent? It's the next 8 bits, right? So it's going to be these bits right here. So what is that? Like, looks like 1011. Okay. So I got this 1000, this 11. So this is binary, right? I want to convert it into decimal and unbiased. So let's convert to decimal, right? I see that the 2 to the 0 bit and the 2 to the 1 bit are on. So let's go do that. So let's go add those. And then of course I notice that the 2 to the 7 bit is also on. Right, so what is this really equal to? It's equal to 2 to the 0, which is 1, plus 2 to the 1, which is 2, plus 2 to the 7, which is the 128, and of course this number is equal to 132. But now we need to remove the bias. So how do we do that? Well, we just have to do 131 minus the bias to get a real exponent of 4, right? And the mantissa is simply just the rest of the bits, right? So we ended off at here. I need to copy down the rest of the bits, but these bits over here are all set to 0, all 18 of these guys. So I don't actually need to include it in my mantissa because it's just not going to change the value in any meaningful way, right? So what is the mantissa for y? It's what is it? 0, 1, 0, 0, 1. Yep. Okay, so this is our mantissa. Let's make it into a scientific notation number. So y is equal to a positive number. So let's make the implied one positive, right? So we have 1 point, and then just kind of copy down the mantissa. So I got 0, 1, 0, 0, 1, and then it's going to be multiplied by 2 raised to the real exponent. Okay, so this is what I have. I have both my numbers in a better form, and now I could do the multiplication right here, right? I could, but I want to make my multiplication even easier, right? I want to not even worry about the binary points, right? I just want to worry about the numbers themselves. So what am I going to do? I'm going to actually shift out the binary points out of both numbers. And how am I going to adjust for that? I'm going to adjust the exponent. So I'll show you what I mean here. So how many shifts would it take to get the binary point out of x, right? It would take 1, 2, 3, 4, 5, 6, 7 shifts. Okay, so what is x really equal to? It's equal to 1, 0, 0, 0, 1, 1, 1, 1. Now times 2 to the 5, just like before, but then minus 7. Minus how many shifts we just had to make. So what is this really equal to? Times 2 to the negative 2. Right, so let's do a similar thing with y, right? What is this really equal to? Let's shift out the binary point. I got 1, 2, 3, 4, 5, right? So I had to shift to the right 5. So what do I actually have? 1, 0, 1, 0, 0, 1. Now multiplied by 2 to the 4 minus 5. So in other words, to the negative 1, right? So now I don't have to deal with the binary point when I'm dealing with my multiplication. I can just look at the numbers, right, and not have to like think where in my result should I place the binary point, right? Not that that would be insanely hard either. It's just I want it to be as easy as possible, right? So let's go ahead and copy down our numbers. Actually, let's not do that. Or I guess I'll do it in a slightly different way here. Right, so here's our numbers. Well, let me go change the template here just so I can kind of like clean things up, so to speak. Okay, so what do we actually have? We got 2 to the negative 2, and then I'll just put like the dot here, and then I have 1, 1, 1, 1, 0, 0, 0, 1. Yeah, looks about right. Okay, and then what else do we have? We have 1, 0, 0, 1, 0, 1. Okay, so that's what we have. And we're multiplying them, right? Of course, I need to add the times 2 to the negative 2 here, or negative 1. Sorry about that. And just to give me the most space as possible, I'm going to kind of shift these over to here. Okay, this is what we have. I'm multiplying these two numbers. How am I going to do it? Right? How am I going to do it? I'm going to, well, let's look at an example, right? So here we got, 12 and 10, right? Or 12 and, yeah, okay, 12 and 10, right? These are both decimal numbers. How do I multiply these guys, right? I just take the 0, multiply by the 2 to get 0, and then I take the 0, multiply by the 1 to get another 0, right? Okay, so now what do? Right? I go to the tens place, and then I multiply 1 times 2, but where do I put the 2? Right? I put the 2 right here. I shift it over 1, right? And where do I put this 1 times 1? I'm going to put it to the left, right? So what I'm really trying to get at is when you move over a place, you have to shift over here, right? So I'm not going to put the 2 here and the 1 there. I want to shift over. So then what does this total to? It totals up to 120, right? Because there's like a sort of implied 0 here, right? So then 0 plus 0 gets you the 0. So that's what we have to use here. That's the sort of implementation, the algorithm that we're going to use to compute this number, right? So this aside, let's go ahead and multiply, right? So I take this 1 times this 1, I get a 1. I take this 1 times this 1, I get a 1. Now, here, the sort of pattern here, or I guess, yeah, sure, we'll call it the pattern. If I have a 1 here, really all I have to do is just copy the contents of this top number into these boxes, right? If I have a 0 here, all I have to do is copy down 1, 2, 3, 4, 5, 6, 7, 8 zeros, right? So you can make it really easy since we're only multiplying zeros and ones, right? So this is how it's going to work, right? I have a 1 here. Let me go copy down the contents of this number, right? So I got 1, 1, 0, 0, 0, 1. Okay, cool. Now I'm at this 0 right here, right? Now I have to multiply 0 times this number, which is just going to give me 8 zeros. But where am I going to put the first 0? Am I going to put it here or am I going to put it here? I have to put it here just to account for the fact that I've shifted over, right? Now I'm in the tens place, so to speak, right? So let's just copy down 8 zeros. I have 1, 2, 3, 4, 5, 6, 7, 8, 8 zeros, right? So then if I'm looking at this sort of hundreds place, I had to do the same thing again, shift it over, make sure the first zero is right here, right? So I got 1, 2, 3, 4, 5, 6, 7, 8. Okay, cool. Now where are we at? We're at this number right here, right? I got a 1. So I had to shift this number over, and then you only have to shift it over by 1, right? So copy down the number, shift it by 1. So I got 1, 2, 3, 4. 1, 2, 3, 4. Okay, cool. So now I'm at this number, just a bunch of zeros, right? So shifted them over though. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, cool. And then we have our last 1, right? So 1, we just copy over everything and we shift it. So I got 1, 2, 3, 4. All right, cool. So this is what we're dealing with. This is what we're dealing with. And the nice thing is that if I'm multiplying this times 2 to the negative 2, and if I'm multiplying this times 2 to the negative 1, they have that common base. So then I can kind of take those two numbers. I can take 2 to the negative 2 times 2 to the negative 1. Since they have the same common base of 2, I can just add their exponents, right? So I know that my final result is going to be some number times 2 to the negative 3, right? But that's a problem for later, right? Let's go ahead and add these. So what do I have? I have 1 and a bunch of zeros, a bunch of implied zeros, right? So if you see blank space here, it's just really denoting a 0, right? So I got 1 and a bunch of zeros. What does that make for? It makes for 0. I can't believe I just said that. It makes for 1, right? Over here, I have 1, 0, and a bunch of zeros, right? So what is 1 and a bunch of zeros again? It is 1, right? And then I guess I'll put the times to the negative 3 here, right? And then what do I have here? I have 1 and a bunch of zeros. So I have 1. Okay, so here I have, in this next column, I have 1, 0, 0, 1. So I have 2 ones. What does 2 ones make for? It makes for 0, carry 1. right? So I'll put my carry right here. Okay, in the next column, what do I have? I have 1, 1. So I got two ones, right? Two ones, of course, makes for 0, carry 1, right? Now in this next column, I have 1, 1, 1. So I have three ones in this column. What does three ones added up give me? It gives me 1, carry 1. Okay. So now in the next column, we have the same situation, right? I got three ones. So those make for 1, carry 1. What do I have here? Three ones again. 1, carry 1. What does two ones make for? 0, 0, carry 1, right? What does one and a bunch of zeros make for? It makes for 1, right? And what does a singular 1 make? It makes for 1. And then two zeros are going to give you 0, and then 1 gives you 1, right? So this is technically the answer, right? But I don't technically want the answer. I want the real answer. So how do I get the real answer? Well, let's go ahead and look at this, and I'll ditch the template for now. Right. So this is technically the answer to x times y, right? But I want the format that the homework specifies, that IEEE 754 floating point representation. So how do I do it? Well, first I kind of want to introduce the binary point again, right? So how do I do that? Remember where we shifted over the binary point, right? The binary point is kind of chilling over here, right? That's why our exponent's to the -3 instead of, say, to the 5 plus 4. In other words, to the 9, right? So let's go ahead and normalize our product. And how are we going to normalize our product? We're just going to shift over the binary point until it hits the spot, right? Because that's kind of how we expect our scientific notation numbers to look like. And the reason why I wanted to get it into scientific binary notation is just because it's going to make it a lot easier to go into IEEE 754, right? So let's go ahead and do that. How many shifts is it going to take me to get to that point? It's going to take me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's going to take me 12 shifts. So I got 1 point, okay, so I'll say it's equal to 1.011011100, and 3 ones. Let's just make sure we did everything all right. So I got 1 here, 0 there, 2 ones, 0, 3 ones, 2 zeros. Okay, it's crucial that we get this right, right? So it's going to be times 2 to the -3. Now, what did we just do? We just left shifted 9 times, or not 9 times, geez, 12 times, right? So I'm going to add 12 since we did a left shift of 12 times, right? And so what is this exponent really? It's 2 to the 9, right? So we have an exponent of 9. This is our normalized product. Now I just need to sort of like put it into that floating point representation. Now, really, the only thing missing here is that I need the the binary exponent, right? Because I have my mantissa, right, and I have my unbiased decimal exponent, but I don't have the IEEE 754 exponent. So what am I going to do? I'm going to take this 9, right? And I'm going to just say, well, we need to add the bias. We need to kind of like do the reverse of what we did before, right? So what am I going to do? I'm going to say our exponent is equal to the real exponent, right? Plus the bias. Remember how we subtracted the bias before? Now I want to add it back, right? What is that equal to? It's equal to 136. Now what is this in binary, right? How I like to do it is I like to just take the greatest power of 2 and then work with that, right? So what is the greatest power of 2 that I can kind of shove into 136? Well, the greatest one that I can think of is 2 to the power 7, so 128, right? Because if you could imagine 2 to the power 8, that's a what, 256? It's too big, right? So what's the biggest value? I guess the biggest power of 2, it's 2 to the 7. So I'll just kind of denote that with a 1, right? Now ask yourself, can I fit 128 plus 2 to the 6, so 64, into 136? No, You can't, right? You would overflow, right? Okay, so let's not try 2 to the 6. Let's try 2 to the 5, right? So does this number fit into 136? No, you're going to go over again, right? At the 128 plus 32, right? It's going to give you like 100 and like, I don't know, 60, right? You're gonna go over. Okay, so let's try 2 to the 4, right? Is 128 plus 16 going to go into 136 without overflow, right? So I got 4, 1, 4. No, it's not, right? Because then you have a 1 here. So, okay, it's not 2 to the 4. Is it 2 to the 3, right? Can I take 128 plus 8 and get something equal to or lower than 136? Well, it actually looks like we just found our best number, right? So I said that 2 to the 7 plus 2 to the 3 is equal to 136. So let's include those bits. So we call this 2 to the 7. I don't want 2 to the 6. I don't want 2 to the 5. I don't want 2 to the 4. I don't want 2 to the actually I do want 2 to the 3, right? And then all the other bits are by default turned off, right? So this is our 2 to the 3. This is our 2 to the 7, right? So that's our binary point, or I guess binary number. That's how I like to find binary numbers when I'm given a decimal value. Okay, but of course you can use the division method. It works just fine, right? Okay, so now we have all that we need. So now I can say that x times y is equal to, now let's assemble our IEEE number, right? So what is x times y? Is x times y a positive number? Yes. Look, we don't have a negative, so it implies that it is a positive number, right? And plus, I mean, just look at x and y, right? X was a positive number, y was a positive number, so of course our final result is going to be positive, right? So how do we denote that in IEEE? We denote it with a 0. Okay, so what's the next step? The next step is to kind of just place your exponent, your biased and binary exponent into the number, right? So kind of copy it down. So I got 1 0 0 0 1 0 0 0, right? Now what do? I look at my mantissa and I also copy that down, right? So I have 0 1 1 0 1 1 1 0 0 1 1 1 and then a bunch of zeros. So by a bunch, how much do I mean? Well, let's look at what we're dealing with, right? I have 1, 2, 3, 4, okay, 8, 12, 16, 24, 25, right? I need 32, right? So I got 26, 27, 28, 29, 30, 31, 32. Wow, did I really just say that? 4, 8, 12, 16, 20, 24, 28. I'm off my meds. That was 28. This is 29, 30, 31, 32. Sorry about that. Right. So now we have our sort of IEEE 754 floating point number, and we just needed to pad with this amount of bits just because well we were just kind of running out of numbers, right? So we just pad to make up for that, and yeah, this is your final result, right? It's in the form that we want, and yeah, that's that. I hope that helped.